Good afternoon. I am Anil Kumar. I'm here again with you in this machine learning to deep learning course. And today I am starting as a first lecture, but this is a second lecture in the series. The topic for my today's lecture is already visible to you, I hope. Journey of classifiers from model based to data driven. So here you will see the basic concept of classifiers, which was developed a long back, and different parameters were considered, different applications were given for that. And then what were the issues you can see in the conventional classifiers? And then the researchers are moving to some new models, which are making model based to data driven. So overall, also you can see in this 5 days program, as I briefed in my inaugural session, that you will go for understanding of machine learning algorithms, mainly the fuzzy based, more focused, and you will have a lot of case studies also during the lectures, like specific crop stage mapping, crop insurance application, specific vegetation mapping, post damage mapping, map transformed class within a given time. Pattern recognition, if you see, basic attributes of humans are to recognize the different objects, right? So that is a first main application, recognition. So human beings basically seeing the patterns on the objects and then they recognize it. So here you can see different objects and they have different patterns, and according to the patterns, human beings recognize the object. Second, if you see for object classification, so direct application of human perception. So here object classification means they can classify here different objects which are lying in this photograph as per the human perception, right? So that means they have some prior knowledge, and using to that they can classify the objects into different groups. Further, you can see vast applications of classification. It can be in prediction or as a stock market prediction, or in the weather case, the rainfall predictions, then control of vehicles, chemical plants, and so forth. Basic requirements for inferring the objects, you can see here. One is your source of light. So here for inferring the objects or to recognize the object, what is required? A source of light is required, so which is falling on the object, then object with unique signature. So when the light is falling, the object is giving the unique signature, and that signature is captured by sensor as a signature. And then on that signature, the interpretation is done in the brain to recognize that this is a baby, for example, as per this photograph. So this is a basic way of inferring the objects as a requirement. You can see here, for example, identifying the famous person, and here a lot of features of the object has been hidden. You can see some shoulder or chin, or here some just eyes with small turban. Still a lot of things are missing and it is quite difficult to recognize. And here also a lot of features are not so much visible about an object to recognize the face, and here also. But here, this is basically there is some different way the person has been represented, like George Bush wearing the turban. So here basically we have to identify nearly the instance once we get the right facial feature of the person. So mainly if we can get the proper features about a person, we can really identify. And for that we have to go for extracting the right feature plays a crucial role in successful classification or recognition. So until unless in the previous, when the things were hidden about a person, so that means we are not getting the right features to classify as a crucial role in successful classification and recognition. So here in this pattern recognition or classification, what is required? First step is we have to go for extraction. So have a digital image of collection of fruits, for example, in this photograph. So there are different fruits, and objective is to classify each piece of fruit. So each piece of fruit we want to classify. So the first step is for extraction. So how do we start? The question is, how do we start this exercise to classify these fruits, and what steps we follow here? Some unique attributes of these fruits will help. So we have to find out some unique attributes of these fruits which can help to identify or recognize these fruits. So what attributes or features we to choose? So here in this fruit case, we may look into the color of fruits like apple, peas or pineapple, then shape of the fruit and weight and so forth, and different parameters, different features we can go for. So we can have here feature measurements from the feature vector. So from feature vector, we can have say color, shape, weight, and so forth. So we may have multiple objects. So the objects form the class vector. And here you can see the class vector with the where n is basically apple, orange, and pear, and so forth. So here n is a basically specific object, and basically the I we can have here the different features of an object. So simple classification problem for this fruit case we can deal in to just simplify, consider only apples and pears. From a collection of apples and pears, we have to measure the color and the roundness of each piece of fruit, or maybe the shape or roundness of the fruit. The measurements will represent typical fruits. So as per the measurements, they will make the fruits very typical fruits. So we can plot this color and the shape parameter on a two-dimensional plane. Say one dimension, each feature we can plot it. So here we can see on the x-axis we have taken its shape, round or not round, and on the y-axis we have taken the color, green, yellow, red, and so forth. So we get here two different unique clustered of fruits for pears and apple. Now we can straight draw the separation line, which can basically separating these two classes. And now you can see we can group as an apple as one class and pears as one class. So this is a feature space where we have plotted these objects using their different parameters. So this is a addition line which is basically classifying the objects as two different classes. So then matching the stored object. So here what we can do once we know the separation of or classification of group of two classes with shorted objects. Now we can go for to map an unknown object. So here this star is an unknown object, and unknown object we can classify while considering its color and roundness parameter. So here, since this object is coming to class 2, we can label that this belongs to class 2. Second, we can also see when we divide the objects in the feature space, we may have linear separation or non-linear boundaries. So in this case, you can see this plus symbols is class 1 and small circles are class 2, and you can draw a straight line. So this is a linear separation. Second situation in the feature space is non-linear boundaries. So here, this is one class and this is your second class. And to separate them, you have to draw some non-linear separation. So here, this separation is a non-linear. So in the ground, in the remote sensing domain also, when you see different classes, the separation can be straight line or separation can be a curved line. Generally, all the classifier or different classification algorithms, they work with the straight line separation. They don't deal this non-linear separation. So if you want to incorporate or handle this non-linear separation in some of the classifiers, you have to use the kernel concept. Specifically, kernel we'll talk about in the coming lectures. Here just I'm mentioning the kernel. The kernel can take care. What the kernel does, it takes the data to higher dimensionality. So here you can see data is 2-dimensional. It can take the data to 3-dimensional such a way that data becomes linear. So once the data is linear, any classifier can handle this type of linear separation. Generally, classifiers do not handle the non-linear separation. So in the data, if there is non-linearity, we have to apply some extra function in the classifier to deal with. So this is a limitation. If you see the conventional classifiers, if you have already heard or used, suppose C means classifier, very simplest one, the first classifier what you came across, C means with respect to the minimum distance. It cannot deal very nicely the non-linear separation between classes. So here, second thing in the 3D feature space, if you plot the different objects, suppose this first and this second, so your here dimension is 3. So if you have 3D feature space, the decision boundary, if you are plotting between these two, it will be 2-dimensional. So by this rule, if you have feature space, say n dimension feature space, so in that case, the decision boundary will be n-1. So the separation line what you draw, it is basically n-1. So here like this, in a 3-dimensional space, you can have a 2-dimensional plane as a 2D plane separating these two classes. Coming to next, two different words. One is recognition and second is classification. So these are two different words. Sometimes we use them very frequently, giving some same meaning. That is not the fact actually. So here, if you talk about classifier, so if you have a group of academicians, maybe like professor, assistant professor, or professor emeritus. So here you can see if you are just extracting professor, so you can have the class for professor. So you can have an example of classification, right? So classification is learn to match. So it is trying to match the similar objects or features with respect to the given data. The form of learning and the process of grouping objects together into class according to their perceived likeliness, so matching. So here a form of learning and a process of grouping objects. So based on learning, we can group the objects together into classes according to their perceived likeliness. So whatever the likeness or dislikeliness is there, similarity or dissimilarity parameter we can consider to match or separate them into different classes. Second thing, if you see for recognition, that is a little different. So here you may have two text words like cat and dog. It looks they are incomplete alphabets in that. So what it is, so you are trying to recognize, not the group basically. So it is trying to recognize that the first one is cat and second one is the. So here you can have the output. So here recognition is learn to reason. In the previous case, learn to match, and here it is learn to reason, a form of reasoning and a process of applying rules and relationship to reduce the decisions. So this is the difference between classification and recognition. So recognition is learn to reason, and here classification means learn to match. Coming to categories of classification in the literature, you can find out. You may have, as per the learning concept, the classifiers can be self-organized training, that is unsupervised classifiers. That means they estimates the decision functions from the input feature vectors of each class. So from the data itself, they divide the data into different classes as per the feature vectors they get. Second is supervised training. Here a teacher signal is known. So here basically the training data is provided to the algorithm, so that the algorithm get trained from using the training data. And then training the data means basically it generates the algorithm parameters like mean, mode, and so forth, or variance, covariance. So these statistical parameters or weights are calculated from the training data, and that way using these parameters algorithm got trained, and then it can divide the data into different classes. Third one, you will see more learning concept I have not yet covered here, but that is a reinforced learning or semi-supervised learning. So this we will see when the deep learning concept comes. So you will see two more learning concepts. But till now, with the conventional classifiers, you have seen only the two training concepts. It can be unsupervised or it can be supervised. Here you can see the very simple algorithm like k-means or c-means, right? It is a statistical algorithm, can be used supervised or unsupervised. Very simple algorithm. You can see one example. If you have a data of some flowers of petals, width and length. So if you plot the length of the petal and the width of the petal, so this group comes, and we want to divide these into number of classes. So here, if we are going unsupervised, so initially we take initialize the guess there are 2 classes. So we take k is equal to 2 here, and at first iteration we get the cluster centers here. So this is unknown, basically cluster centers which has been assumed initially, and we can say their cluster centers are here, and we can say this is a class 1 and this class 2 red dots. The moment further iteration goes on, so we found the cluster center is here, it is moving, its position has changed, the red one and the blue one is here. So we can say this is the blue dots are the cluster 1 and red dots are the cluster 2. At further iteration, at iteration 3, the cluster centers are moving further. So here you get the red cluster here and the blue cluster center is here. And then it can say this is your blue cluster and this is your red cluster. And if you go for further iterations, iteration 4, the cluster center is moved here. So red one is here and blue one is here. So it is telling this is your blue one and this is your red cluster. And further at the 5th iteration, you can see the cluster center. It is quite close to the true value. Not exactly, but very close. And now you can tell that these blue dots are cluster blue one and this is for the cluster red one. So this is a basically unsupervised approach. Initially, the cluster centers were assumed here for 2 clusters, knowing the data we want to divide into 2 clusters. So after assuming that, it is iterating with respect to a minimum distance criteria, and new cluster has been calculated as per each cluster got the samples. Further here you can see we can try to do study that in this given data, do we have only 2 clusters, or we can have we can divide the data into more clusters. So as through unsupervised approach, so we can say k is equal to, we can start with 2 initially, and later on we can say cluster 3. So that means the algorithm is assuming there are 3 cluster means here, and then it is dividing the data into 3 clusters. Then it is going for 4 clusters. So here it is assuming the 4 cluster center. Using this 4 cluster center, it is dividing the data using the minimum distance criteria into 4 clusters. It has gone to 5 clusters. So you can see how the data has been grouped into 5 clusters. So here we can have the elbow point. So elbow point is a concept which tells or which helps us to find out in a given data how many number of clusters we can extract. So here, if you see, it is basically minimum at this point, and this is the score coming out from elbow curve. So here at this point, it tells that maximum 3 clusters we can extract from the given data. So if you have remote sensing image and you do not know the about the area, what are the different classes present in the given study area and how many classes we can extract from this given image. So what you can do, you can apply the elbow point concept to find out how many number of clusters or classes are present from a given image which can be extracted for a given study area. Next little bit I will just cover, but we'll have more detailed lecture on training of the algorithm. So first is supervised learning. So here you may have unknown data to divide into different groups. And if you say here some teacher signal, that means training data or samples you are passing. And here if it says A belongs to C1, then it is out 1. If A belongs to C2, then it's out -1. So that the label is defined. And with this criteria, you can divide this all signals to class A or that is 1. If it is 1, that is C1 class, and if it is -1, then it's C2 class. So here this basically forced output labels as dictated by the teacher signal. So as per the teacher signal, you are dividing the data as a dictated approach. So here you can see for the remote sensing data, if you have a k number of bands here, so you from each band you get 1 pixel value. So this one basically feature vector, so pixel vector rather, and applying the training data here, and you can generate the features from each that data, and then you can label it that this is for your class F, this is your U, this is water or W, and this is S, this is U, and like that. So you can have a thematic map for urban, forest, water, and soil, and so forth, while applying the training data. And the training data, you have samples as well as the labels. So you can have the samples for class water. Water is a label, samples for forest, and forest is the label. Samples for urban, and urban is the basically label, and sand is basically again label, and you have the samples for sand. So that way you can have the output in the as a thematic map. The basic classifiers, if you see in the literature for supervised or mainly unsupervised classification approach, mainly the statistical classifier were the first basic algorithms. Typical teacher signals, you can have XML classifier. So training data defines the statistical parameters of the statistical distribution. So if you are taking the statistical algorithm, it generates the statistical parameter that tells how the data is distributed, the probability of an unknown pixel being one of the class. So here, as per the probability, you can divide or label unknown pixel to a particular class. If an unknown pixel has brightness values within the wetland region, it has a high probability of being wetland. So one way, if you see the brightness value of a pixel is very close to the wetland, so it has very high chances that that pixel belongs to wetland class. So here you can see the working of, say, maximum likelihood classifier as well as minimum distance criteria. So a pixel X would be assigned to forest because the probability is greater for forest than agriculture. So if you are calculating the probability for forest and agriculture, and if the probability of forest is more, you can see it's quite more compared to agriculture. So you can label that pixel to forest. In the case of minimum distance classification, if the distance is minimum for agriculture, then forest, so that unknown pixel can be labeled to class agriculture with respect to minimum distance criteria. So these are the very basic algorithms which were used intensively in the digital image processing for remote sensing data to prepare the thematic map, mainly the maximum likelihood classifier MLC. So here you can see one example of a satellite image which has been classified. This is the original image having some few bands, and here you can see the few classes has been generated: urban, then grass here, then forest, then water, and further some maybe cloud patches also may be extracted. So here the very simple algorithm, if you see, you have C means, you have Mahalanobis distance, you have parallelopiped classifier, or it is also called box classifier, and the fourth one is MLC, maximum likelihood classifier. These are the four very basic statistical classifiers used for so many decades for preparing the thematic map. Some of the limitations you can see or drawbacks in these statistical methods, which I'm listing here. One is assumption of normal distribution function of objects grave level. So here, when we apply, say, suppose maximum likelihood classifier, we have to take care my data is normal distribution function. That follows the normal distribution case. Secondly, works largely well for images of resolution, say about greater than pixel size 10 meter. When the pixel size is more than 10 meter, so these algorithms works very nicely. Second is finer resolution data will have other interpretation parameters leading to classification error, and which are unexpectable for many applications. So when the resolution of the image is very high, maybe less than a 10 meter, maybe the pixel size going to say 5 meter or 3 meter or 1 meter or less than 1 meter. So many other parameters are dominating, and that's why these basic classifiers may not give you very good results. So what are the parameters? Basically, from these algorithms, we are using digital number, that is a color of the image, one way we can say. But as the pixel size is decreasing, you can see the texture is more dominating, as around if the pixel size is 20 to 10 meters. So you can see texture is more dominating than color. Color is more dominating when the pixel size is bigger than 20 meter. And when the pixel size is 10 to 20 meter, texture is more dominating. And when the pixel size dropping from 10 meter, then less than 10 meter, you can see the shape is more dominating as 3 meter, 1 meter or less than 1 meter. So as the shape and texture is dominating, the performance of these classifiers will drop. Terms in classification jargon, one is parametric classifiers. Parametric means there is no any extra coefficient in the classifier. Whatever parameters are given, we can calculate them from the training data like mean, standard deviation, minimum, maximum, variance, covariance, and so forth. So these are standard statistical parameters which we can calculate from the training data. And once these parameters are calculated, we can directly get the result. We don't have to optimize any other parameters. So that is basically approach of parametric. Since it is using statistical parameter, so we can also say these algorithms are statistical algorithms. And since they are using only pixel information, so we can say these algorithms are pixel-based classifiers. Then you can have non-parametric classifiers, which basically learns from objects to decide and to create polygons in feature space, like your ANN, or where there are so many free parameters. We do not know what can be the strategy for these parameters for different data sets and for different problem. But in here, there is a fixed strategy. You can use it for any image and for any study area. The strategy will remain same, parameters will remain same, but here the parameter value changes as per the problem we are dealing. So type of classifiers, if you see, and you can compare with the past with present. Previously, there were pixel-based classifiers which were using only DN information, but today you can have object-based classifiers which are using shape, texture, hierarchy, and so forth. So many parameters about the object you can use, like if you have 1 meter image or less than 1 meter pixel size image, you can see the shape, texture, hierarchy of the within the object very nicely. Then statistical classifiers, which is used from the very beginnings, like k-means, maximum likelihood classifier, box classifier, then fuzzy classifiers. So these are statistical classifiers because they are using statistical parameter. It can be mean, variance, covariance, minimum, maximum, and standard deviation, and so forth. But second category, as per the statistical one, it can be learning parameters, which are not using statistical parameter, but they are using weights. The classifiers, very basic one, can be ANN, artificial neural network, convolutional neural network, CNN, RNN, recurrent neural network, and so forth. And they are hybrid versions. Then third category, you can see statistical learning. So first is statistical, second is here learning, and third is statistical learning, like support vector machine. So in the support vector machine and the rule-based classifiers like decision tree, they are basically statistical learning. They use sometimes weights as well as statistical parameters like mean, mode. Then fourth level of classification, you can see here hard and soft classifiers. So in your data, if you have pure pixels, that means in one pixel you have only one class. So you can apply the hard classifiers. Your answer will be 1 or 0. But if you have some mixed pixel, that means there is more than one class present. Suppose forest and water. So you cannot apply the hard classifiers. You have to go for soft classifiers. And soft classifiers are like that. They can tell how much is forest. It will tell forest is 0.6 and water is 0.4. So this 0.6 and 0.4 is degree of belongingness to the class. And today the trend has gone. The people have implemented these classifiers such a way that any classifier you can work, or you can use them as soft and hard. In the commercial softwares also, like if you see NV, there are so many large number of classifiers has been implemented, starting with C-means, MLC, decision tree, ANN, support vector machine. So their output, you can save them as a hard or soft. So they are soft, it is called as a rule images. The next is basics to latest classifiers. Now here, if you see from a very basic classifiers to the latest one, which is there nowadays in the literature, large number of classifiers. The basic one can be C-means, which is working on with a minimum distance criteria, and it was designed for unsupervised case. But today you can see in the commercial tool, you can use it for supervised also, because it is very simplest algorithm. It just calculates the mean parameter from the given sample of a class as a supervised. And using that mean parameter, it can calculate the distance for each unknown pixel, and it can tell the distance is minimum for which class. And as per the distance minimum, that pixel is labeled to that class. Second is parallel piped or box classifier. This creates the box using the mean and standard deviation or minimum and maximum parameter from the training sample of each class. And using that, it creates the box. Whatever pixels are lying inside the box, they are labeled to that class. Third is maximum likelihood classifier. It is basically working on probability, and unknown pixel having the maximum probability for a particular class. So that pixel is labeled to that class. Then second category as a decision tree approaches, you can see decision tree classifiers, and today very largely it is used called random forest. And second, its modified version is called classification and regression tree, that is CART. So these are two and further versions you can further explore in the literature for decision tree classifier. Here it is requiring the rule to be generated, and then only you can use these decision tree classifiers from a given training data. Second is fuzzy domain. If you have mixed pixels, that means you are not sure all the pixels are pure. And since there are boundary of two classes, so if you see the boundary pixels, they are mixed pixels, they are representing the two classes. So these are the mixed pixels. Sometimes the class size smaller and the pixel size bigger. So again, you will have mixed pixel here, right? This is water and this can be forest. So due to these two causes, one is boundary representation, second is class size is smaller than the pixel size, you may get the mixed pixels. So how to handle these mixed pixels? We have to go for soft classification. And for that, the best solution is you have to go for fuzzy based classifier. In the fuzzy domain, the very basic algorithm which was developed by Bezek and the fuzzy concept was given by Zade. So here the FCM, fuzzy C-mean classifier. So this is a modified version of C-means. So here you see the one extra word fuzzy. Fuzzy C-means, right? So this is also working on the distance criteria, but output you can generate in the form of membership value. So here it will tell the water is 0.3, and forest is 0.7. So this is the degree of belongingness. Water belongs with 0.3 degree and forest belongs with 0.7 to the forest class. So here you can get straight membership value using the membership function from this FCM or fuzzy C-mean classifier. Their modified versions are PCM, possibilistic C-mean classifiers, noise clustering NC, IPCM, integrated possibilistic C-mean improved possibilistic C-mean classifier, and then MPCM, modified possibilistic C-mean classifier. And here there are few classifiers out of these 4 and 5 classifiers which can give you single class. One is PCM, second is NC, third is MPCM. They can give you single class. If you give the signature data of say one class, you will get the output as a one class output only. Then you can have the further classifiers which were designed maybe to handle the subpixel concept or hyperspectral like SAM, spectral angle mapper, or linear mixture model or non-linear linear mixture model. So here these are the classifiers designed for subpixel classification or hyperspectral. SAM is mainly designed initially for hyperspectral data processing, and linear mixture model and non-linear mixture model was designed, if you have seen the literature around 20 years back, subpixel concept. So here subpixel concept, but today the subpixel concept has been replaced. Today I can say any classifier can be used for subpixel concept, and people talk about more very common terms, soft classification. Meaning is same. Then further, if you move, you can have the learning based classifiers like ANN, artificial neural network, then CNN, convolutional neural network, RNN, recurrent neural network with deep learning concept. So last 5 years, you can see more extensively the deep learning models, CNN, RNN, which are very simple one and very basic. You can have the hybrid modified versions of these. And before that, ANN was used for last so many decades, but the last 10 years, you can see the deep learning concept has came as a modified version of ANN model onwards. Then further different type of classifier, it can be object-based classifier. If you are using very high resolution image like at 1 meter or better than 1 meter, you can see very different interpretation parameters from the image. One is shape, texture, contextual information, and of course the color or the pixel value, and then hierarchy. Hierarchy means you may have very big patch of forest. Within that, you may have deciduous trees and the coniferous trees. So this is hierarchy. So you can have the hierarchy concept also. And all these parameters you can, if you incorporate, then it talks about as a object-based classification. That means we are using more than one variable or more than one parameter of an object. Then these classifiers, which are simpler in nature, you can use them as supervised or unsupervised. Not all the classifiers to be used as unsupervised, but yes, here all these classifiers you can use supervised, but not all the classifiers listed here you cannot use them unsupervised because their parameters are complicated and you cannot estimate, you cannot refine these parameters through unsupervised. So there are limited classifiers which can be used for unsupervised, like here C means, here FCM, you can use it. Even here for in the fuzzy domain, you can use all the classifiers as unsupervised. There is no issue. In ANN or CNN, you can use unsupervised, but not the similar model. There are category of models to be used supervised, and there are different category of models which are used to be used for unsupervised. Of course, these classifiers, all these classifiers, you can use them as a hard or soft. So here, just I talked about the total classifiers which are present in the literature. It can be different type as per supervised or unsupervised concept, that is learning concept, or it can be say the statistical category or pixel based, or it can be parametric or non-parametric. It is just using one parameter like pixel information, or it is using large number of parameters from the object like shape, texture, contextual information, pixel information, or hierarchy. So, and they can be used as supervised or unsupervised, but not all the classifiers can be used unsupervised because there are so many parameters which cannot be refined once we assume the parameter through iteration. Like mean you can refine as number of iterations if you run, mean can be modified, but variance covariance, one of the parameter, cannot be modified. If you see maximum likelihood classifier or even the distance classifier, the very general distance formula you can have like d square. If I take, you can define it as xi minus xj transpose, and this is bar, and this is A inverse. Then this is xi minus xj, and this is bar. So this is general distance equation, which can be defined in 3 different norms depending upon A inverse. So here, if I take A inverse, A inverse is a weighted matrix. If I take this as a unit matrix, then this distance becomes Euclidean distance. If I take here variance covariance matrix, then this becomes Mahalanobis distance. So Mahalanobis was an Indian academician in Bengali from Indian, that is ISI Institute in Calcutta. I think that is Indian Statistical Institute, Calcutta. So he was there, and he has proposed this Mahalanobis distance, and on his name VC parameter has been incorporated, and the distance name was given Mahalanobis distance. The third version of A inverse, you can use diagonal variance covariance. Okay, so but in the commercial tool, if you see maximum likelihood classifier, it is using only the mean and variance covariance. C means classifier, it is using only Euclidean distance. That's why it is using the unit matrix, and that's why the distance become Euclidean. But in the literature or on the different papers, you can see in C means you can use the distance can be Euclidean distance or Mahalanobis distance or diagonal variance covariance distance. Same way, these three versions we can apply in the fuzzy based classifiers because they are using distance only. But we can but in the literature you don't see in the literature you can see all these distances we can incorporate in the fuzzy based classifier. But in the commercial tool you don't see that it is using all the three type of matrix forms. It is using only the Euclidean norm. Second thing I mentioned in the my previous slides in this lecture, that how to deal the non-linearity. So for non-linearity we have to apply kernels. So here these fuzzy based algorithms or statistical based algorithms, we can insert the kernel. So here if you see MLC, you can have a probability with kernel concept. So you can have K MLC. That means it is not using the simple distance, it is using the kernel in place of distance. Same way for C means, you can use a kernel, so it becomes K C means. Mainly in the literature people have used with the fuzzy based classifier FCM, they are using basically K FCM. That means they have introduced kernel in FCM so that it can deal the non-linearity between the classes. So you may have two classes like this and there's a non-linear separation. So how to handle this non-linear separation? So for that we have to use the kernels. So this is all about I want to talk about in today's lecture. Now I can take up the questions which are there. Just in this COVID time, we published dedicated book on fuzzy machine learning algorithms for remote sensing image classification in 2020 with the CRC press. It is a focused book on fuzzy based algorithms as well as incorporating the one chapter on deep learning for image classification and different issues. Also how to deal with the temporal data to process very unique single class, and that what I'm going to